Acids and bases are everywhere. They're used to make foods, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides, even paper. Our stomachs are very acidic, our blood is slightly basic. Our proteins are made up of amino acids, and the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules, acids and bases were defined by how they behaved. Acids tasted sour and corroded metals. Bases felt slippery and could somehow counteract acids. When molecules dissolved in water interact, they're exchanging two main currencies with their surroundings: protons, also known as hydrogen ions, and electrons. Depending on how a molecule is composed or shaped, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has two protons but is generous enough to hang out with just one. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules has exchanged currency with water. As you might guess, we label these acids and bases weak, but in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, that is a weak base. So it doesn't take much to be an active player in the chemical economy. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And when a proton deposit customer, that's an acid, and a proton withdrawal customer, the base, shop at the same time, their net effects on water's account may cancel out, and we call this neutralization. Now, certain molecules can behave as acids or bases without water, but that's another story. Let's end by saluting water as the resilient and fair banker for acids and bases. It's always open for business, doesn't charge interest, and will never foreclose on your molecules. Which is more than I can say for wah wah.